Hey guys, so here's another problem from this week's problems on thermochemistry, a standard enthalpy of formation problem. So in your textbook, and I'll show you right now where, in the appendix, in most textbooks in the appendix, they have what's called a selected thermodynamic data tables. And these are really long tables. It's for individual elements and molecules, all sorts of stuff. So you'll see that there's delta HF, delta G, S. We'll learn what these are later, but right now we're going to focus on this delta HF, which is the enthalpy of formation. And there are tons and tons and tons of lists. Some are more complete than others. You'll see this one is a couple pages long in your appendix. And we're going to use this information to figure out how much energy is needed to create these molecules. The one thing you should recognize, and I'll try and look for an example really quick. Here's one. Great. So mercury, I don't know if you can see that. Actually, here's a better one. Sodium solid, right? Notice it's Na from the element. Same thing you'll see on the periodic table. Solid is how you would find this in nature at standard conditions, 25 degrees Celsius and 1 atm. The delta HF is 0, right? Sodium ion is different. It's got a negative value. And sodium in these molecules, they all have values as well. So what this is telling you, and what's the important thing to recognize, is elements, even diatomics like N2 gas, right? There's nitrogen gas. Its standard enthalpy of formation is 0 at the conditions of 25 degrees Celsius, 298 K, and 1 atm. So elements that are found in nature in their standard states, they are going to have this delta F of 0, and that's really important to remember. Everything else, if this was actually liquid nitrogen, that would be a different value. So it's not the same. It has to be the standard state that is found at the conditions of 1 atm and 298 K. So we use that table to figure out all the delta H's of formation for these individual molecules, and then we're going to use a really simple equation and plug and chug to figure out the delta H of a reaction. Okay, the equation looks kind of intimidating, and this is on your equation sheet for the AP exam, so you don't need to memorize it, but I just want to write it out so you can look at it really quick. So it's sigma n delta H formation for your products minus the same thing and delta H of formation for the reactants. So there's a lot of symbols here, okay? This really simplifies to simply what's the delta H formation of the products minus the delta H formation of the reactants. The N is a symbol we've talked about before. It's moles, right? So we have to take into account moles from the balanced chemical equation. Okay, and that's not tricky. We probably were already thinking that. And then sigma just means sum. So we add up the sum of all the moles of all of the reactants, right? And subtract that away from the delta formation, considering the moles and adding up all this for the products. So we figure out the products delta H formation, add that all up, subtract away from the reactants. It's as simple as that. So here's how we would do this one. So delta H, a reaction. I'm going to first look up my products. Okay. So let's go to our table. I'm not going to grab it right now. I've already got these values here on some notes on the side here. So I see that the delta H, let's actually skip this part. Let's figure out the delta H of formation for everything. So let's do it for NH3. What's the delta H of NH3 gas? Make sure you pay attention to states, guys. That's a part I often forget about. States matter. Sometimes the delta H of formation for a different state is going to be a different value when you look it up in that appendix. So I'm going to look this one up and see that the delta H formation for NH3 gas is negative 45.9 kilojoules per mole. Okay, delta H of formation for O2 gas. What do you think, guys? O2, standard formation of delta HF of O2 gas. That's how we find it in nature, right? So it's going to be what? 0. Okay, and then delta H of NO gas, that's a molecule, so that one's going to have a value. NO is positive 90.3 kilojoules per mole. And again, I'm getting these numbers here from that appendix. And then the last thing is water. Delta H of formation of H2O. But notice it's water gas. If you looked up water liquid, it'd be a different value. So water as a gas is negative 241.8 kilojoules per mole. All right, so now that I have all the delta H formations for each molecule in my equation, I'm going to multiply by the coefficients for each one. So NH3 was 4 moles. Okay. It doesn't matter for O2 that I have 5 moles because when we multiply by 0, we're just going to get 0. But I'll put it there just to show the idea. NO is 4 moles. And then I have 6 moles of H2O. Alright, so let's do this math. And then we'll just plug it into this equation and be done. So negative 45.9 times 4, negative 183.6 kilojoules now. I've canceled out my moles, so I don't have kilojoules, and this was for NH3. This is going to be 0 kilojoules because I'm multiplying by 0. 90.3 times 4 gives me positive 361.2 kilojoules. Then negative 241.8 times 6, negative 1,450.8 kilojoules. All right, so let's put it into this equation. Delta H reaction equals. All right, so I'm going to sum. I already factored in the moles, so I don't need to worry about that. I'm going to add together my products. My products, again, were the NO and the H2O, these last two pieces. So I'm going to say, all right, 361.2 kilojoules plus negative 1,450.8 kilojoules. That, again, is my products. And I'm going to subtract away the reactants. Okay. Sorry, guys. Guess I got a little out of frame there. Hopefully we can see everything now. All right, so then I'm going to subtract away the reactant information. That's just negative 183.6 kilojoules plus 0. I'm not going to even put it in there because it's not important. Adding zeros not going to do anything to this number. So let's simplify and do it. I'm going to deal with this first, 361.2 plus negative 1450.8 is negative 1,089.6 minus negative 183.6. Minus, subtracting a negative number means adding, right? So just be careful when you're putting all this together. That's why I'm doing it in steps. And I finally get negative 906 kilojoules as my answer. So again, what is this? This is the delta H of a reaction using this equation for the standard enthalpy of formation of all the products, subtracting away the reactants.